Welcome back to The Deep Dive, the show where we distill complex information into those potent insights that truly make you well-informed.
Glad to be back.
Today, we're plunging into a world that might sound simple at first, but is in fact one of organic chemistry's fundamental superpowers.
Oh, yeah.
Imagine having the ability to add hydrogen or electrons to a molecule, transforming its very identity. That's exactly what we're going to explore. The surprisingly intricate and profoundly practical world of reduction reactions.
That's right. And our mission in this deep dive is really to extract the most important nuggets of knowledge from Advanced Organic Chemistry Part B reactions and Synthesis, the 5th edition.
A classic text.
It really is. We'll unpack the major reaction types, crucial synthesis strategies, and the detailed mechanisms behind them. And we'll always keep an eye on their practical applications.
And we'll define the jargon as we go, right?
Yeah.
No need to worry as some terms sound intimidating.
Absolutely. We'll demystify any technical terms. Think of this as your essential shortcut, to understanding how chemists precisely manipulate molecules for groundbreaking discoveries, from pharmaceuticals to advanced materials.
Okay, so let's start at the very beginning. What is reduction in organic chemistry? At its core, it means one of two key things. Either you're adding hydrogen atoms or electrons to a molecule, or conversely, you're removing oxygen or other electronegative atoms. Things like halogens sometimes.
Exactly. It's a fundamental process, really underpinning the creation of everything from life-saving drugs to the cutting-edge materials that shape our world.
And to make these transformations happen, chemists rely on a whole toolkit, right? These reducing agents.
A diverse cast of chemical tools, yeah. We'll focus on the most synthetically important ones. First, there's just plain old molecular hydrogen, H2O, but it usually needs some help, often used with a catalyst.
Right. Doesn't do much on its own usually.
Not typically for these transformations. Then we have the hydride derivatives of boron and aluminum. These are like tiny, highly specialized delivery trucks for hydrogen atoms.
Ah, I like that analogy, like sodium borohydride.
Exactly. Sodium borohydride, lithium, aluminum hydride, those are the big ones. Each with its own unique personality, its own reactivity.
Fascinating. And beyond those, what else is in the toolbox?
Well, we move to the more specialized but incredibly versatile silicon and carbon-based hydride transfers. Think of these as maybe more nuanced ways to deliver that hydrogen.
Okay.
We also have metals, just plain metals sometimes, like lithium, sodium, or zinc. These act as powerful electron donors. They just give electrons away.
And it can break bonds.
It can break existing bonds and even forge entirely new carbon connections, which is, a huge deal when you're trying to build complex molecules from simpler pieces.
Wow, okay.
And finally, we'll look at hydrogen atom donors. Agents like silanes or stannanes, tin compounds that operate through these fascinating free radical mechanisms. Completely different pathway.
So, a lot of ground to cover. How are we structuring this?
Well, our source material breaks these reactions down into several logical categories, and we'll basically follow that path. We'll start with adding hydrogen to multiple bonds, then move through carbonyls and other functional groups, explore the different kinds of hydride donors in more detail, and wrap up with those radical and dissolving metal reductions.
Sounds like a plan. A comprehensive look at the chemist's reduction toolkit. All right, let's dive into our first major section. The addition of hydrogen at carbon multiple bonds. You call these the synaddition specialists in the outline.
That's right, because a key feature is how the hydrogens add.
Okay, first up, the absolute workhorse reaction in this field. Catalytic hydrogenation using heterogeneous catalysts. If you want to saturate or reduce a carbon double bond, turn an alkene into an alkene, this is usually your first thought.
It really is the go-to method. It's prized because it's generally fast, it's remarkably clean, typically produces very few unwanted byproducts, very efficient.
And heterogeneous means the catalyst is in a different phase from the reactants, right? Like a solid catalyst in a liquid solution.
Precisely. These reactions don't just happen randomly in the solution. They occur on what you can imagine as a kind of factory floor, the solid surface of a transition metal. Think platinum, palladium, rhodium, nickel.
Usual suspects.
Usual suspects, exactly. These catalysts might be finely dispersed solid particles, or maybe they're spread across inert support materials like carbon or alumina. The whole point is to maximize that reactive surface area where the chemistry happens.
So how does this surface dance actually work? I know solid surfaces are complex, but what's the general picture?
It's a good question. While the exact choreography can be intricate, the general steps are fairly well understood. First, you have hydrogen molecules, H0, landing on the metal surface and sticking. That's adsorption.
Okay.
And when they stick, they actually break apart, forming individual metal hydrogen bonds. Think of the surface almost like sticky flypaper, but one that pulls the H molecule apart.
Got it. Hydrogen atoms ready on the surface. What about the alkene?
Next, the alkene also adheres to the catalyst surface. It forms what's called a pi complex. Basically, the alkene's electron clouds, the pi bond, interact with the metal's orbitals. You can sort of picture it lying down flat on the surface.
Okay, so both reactants are now stuck to the metal.
Right. Then, a crucial step. One of those adsorbed hydrogen atoms, now kind of like a hydride on the surface, transfers to one carbon of the double bond. This temporarily links the molecule to the metal via a carbon-metal sigma bond.
Ah, okay. One hydrogen added.
And then, usually pretty quickly, a second hydrogen atom transfers to the other carbon of the original double bond, forming the fully saturated alkane.
And then it just floats off.
This newly formed alkane then detaches or desorbs from the surface, leaving that catalyst site free for the next alkene and hydrogen molecules to come in. It's a cycle. That's what makes it catalytic.
Makes sense, but you mentioned a twist. It's not always that straightforward.
Ah, yes, the isomerization twist. Here's where it gets really interesting, and it's often a surprising thing for chemists just learning this. Sometimes the metal catalyst can actually pull off a hydrogen from a position next to the double bond and a lilac hydrogen.
Okay, what does that do?
It forms a short-lived intermediate called a pi-allyl complex, and this little detour explains why you might observe double bond migration during hydrogenation. You start with the double bond between carbons 1 and 2, and you end up with some product where it's between carbons 2 and 3.
So the double bond can actually move around on the catalyst surface before it gets reduced.
Exactly, or before it comes off unchanged. It also accounts for things like isotopic hydrogen exchange, where if you use deuterium, DRO, you might find deuterium atoms swapped into positions you didn't expect. These side reactions can sometimes compete with the main reduction. It reminds us that even seemingly clean reactions can have complex things happening under the surface.
Fascinating. Okay, let's talk stereochemistry, controlling the precise 3D shape. You mentioned the SYN rule earlier.
Yes, the SYN rule. SYN. It's a fundamental principle here. In most catalytic hydrogenations, both hydrogen atoms add to the same face of the double bond.
So they come in for the same direction.
Precisely. This is called SYN addition, and it's absolutely critical for controlling the final molecular architecture, the 3D shape. The intermediate molecule, while it's on the catalyst, remains bonded in a way that preserves this spatial relationship.
And which face do they add to?
Typically, the molecule approaches and adsorbs onto the catalyst surface from its less sterically crowded side. It just fits better that way.
Like finding the easiest parking spot.
Exactly like that. So hydrogen usually adds from that less crowded face. However, while SYN addition from the less hindered side is common, it's not an absolute law. You see it very strongly in certain rigid or sterically demanding alkenes, which makes the products predictable.
But there are exceptions.
Oh, yes. Sometimes you might even see hydrogen add, perhaps surprisingly, from the more substituted or hindered face.
Why would that happen?
It's often due to subtle electronic effects, like rehybridization that occurs when the double bond interacts with the catalyst surface. But what's even more powerful synthetically is how polar groups on the molecule, things like hydroxyl groups, can actively direct the addition. They can sort of grab onto the catalyst too.
So the OH group can steer the hydrogens.
It can. It can guide the molecule onto the catalyst surface in a specific way, forcing the hydrogen addition to happen from its face, the face where the OH group is. This is a really powerful tool for chemists to steer the reaction exactly where they want it to go stereochemically.
That leads nicely into substituent directive effects. Tell us more about that.
Right. The presence of these polar functional groups can dramatically alter the stereoselectivity because they interact, they coordinate with the catalyst surface. The hydroxy group is a particularly strong director, often ensuring hydrogen gets introduced from the same face of the molecule as the hydroxyl.
Can you give an example?
Sure. Consider two molecules with very similar shapes. Maybe one's an alcohol and one's an ester in the same position on a ring system. The alcohol might strongly direct the hydrogenation to give a cis product, where the new hydrogens are on the same side as the alcohol, but the ester, which doesn't coordinate as well, might lead to a trans product.
Wow, that's a huge difference in outcome just based on swapping an alcohol for an ester.
It's a dramatic difference, yeah, and it's all controlled by that functional group's interaction with the catalyst.
Does the solvent matter here?
Absolutely. This directing effect is highly solvent-dependent. It's usually strongest in nonpolar solvents like hexane. If you use strong donor solvents like ethanol or DMF, the solvent molecules themselves can compete for those coordination sites on the catalyst.
Ah, so they kind of swamp out the directing effect of the group on the molecule.
Exactly. It's like a loud crowd drowning out a whispered instruction. You lose that fine control.
And is there a ranking? Are some groups better directors than others?
Yes, studies on complex ring systems have shown a pretty clear hierarchy. Things like amino groups, hydroxyl groups are strong directors. Others like esters, carboxyl groups, amides are generally non-directive.
What determines that ranking?
It seems that Lewis specificity is a key factor. Basically, how good a group is at donating electrons to form a bond with the catalyst metal. Groups that are good Lewis bases tend to be strong directors. Understanding this allows chemists to actually design molecules with built-in steering wheels for specific hydrogenation outcomes. Tag 1.2. Hydrogenation using homogeneous catalysts.
Okay, so that's the world of solid heterogeneous catalysts. But what about homogeneous catalysts? You said these are different.
Right. Unlike the heterogeneous ones, which are solids, homogeneous catalysts are soluble transition metal complexes. They dissolve in the reaction solvent, operating in the same phase as the reactants.
And why is that significant?
Well, that solubility is a real game changer mechanistically. Because everything is dissolved and mixed uniformly, it allows for a much more precisely described picture of how the reaction happens. We can study the individual steps much more easily than on a complex, solid surface.
Is there a famous example?
Absolutely. Wilkinson's catalyst is the classic one, a rhodium complex with triphenylphosphine ligands. It really revolutionized organic synthesis when it was discovered.
So how does the mechanism work here in solution?
With homogeneous catalysts, it's often described as a beautifully defined catalytic cycle, a sort of molecular dance. The alkene first forms a pi complex with the metal, similar to the heterogeneous case, but now it's with a discrete metal complex in solution. Then, hydrogen adds to the metal in a step called oxidative addition. This changes the metal's electron count and its formal oxidation state.
So the hydrogen attaches to the rhodium first.
Yes. Following that, one of those hydrogen atoms now attached to the rhodium transfers from the metal to a carbon on the alkene. This forms an intermediate where the molecule is still attached to the metal, now via a sigma bond.
And then the second hydrogen.
The final step is usually a second migration of hydrogen, or sometimes a step called reductive elimination, which forms the fully saturated product and, crucially, regenerates the active catalyst. That's the cycle. It goes round and round.
And those phosphine ligands you mentioned on Wilkinson's catalyst, are they just spectators?
Oh, not at all. The organic ligands attached to the metal, like phosphines, are absolutely critical. They stabilize the different complexes in the cycle, and they fine-tune the metal center's electronic properties and reactivity. They're like molecular dimmers, controlling how reactive the catalyst is.
Do these homogeneous catalysts also show directive effects from polar groups?
Yes, absolutely. Similar to heterogeneous catalysts, polar functional groups often control the stereochemistry with homogeneous catalysts, directing hydrogen delivery cis or to the same face as themselves.
Any specific examples that stand out?
The Crabtree catalyst, which is an iridium-based system, is a prime example. It's renowned for its excellent stereoselectivity, and it's strongly influenced by hydroxyl, amide, ester, and even ether substituents nearby.
How does it achieve that selectivity?
This powerful selectivity likely comes from the catalyst's remarkable ability to coordinate with both the directing group on the molecule and the double bond at the same time.
Wow, like it has two hands grabbing different parts.
Exactly. It grabs the directing group with one hand and the double bond with the other, holding the molecule in a very specific orientation so the hydrogen can only add in a precise way.
What are the main advantages, then, of using these homogeneous systems?
Well, they often offer higher selectivity among different functional groups compared to heterogeneous catalysts. For instance, you can sometimes selectively reduce an unconjugated double bond while leaving, say, a conjugated one untouched.
That's useful.
And even more dramatically, you can often reduce a double bond without affecting a nitro group. Nitro groups are usually rapidly reduced by heterogeneous methods like palladium on carbon. This ability to pick and choose which part of a complex molecule to modify is incredibly valuable, especially in long, multi-step syntheses.
That selectivity sounds key. Any examples in complex molecules?
Definitely. In the synthesis of complex natural products, like the fragrance molecule armascone, homogeneous catalysts like Crabtree's delivered really high yields with minimal unwanted side reactions. Specifically, they avoided racemization, the scrambling of stereochemistry, which was a problem with some heterogeneous catalysts in that case.
So better control, higher precision sometimes.
That's often the case, yes. Especially when you need that exquisite level of selectivity. Hashtag tag 1.3. Enantioselective hydrogenation, building mirror images with purpose.
This precision leads us naturally to perhaps one of the most sophisticated applications, enantioselective hydrogenation. This sounds important. What's the goal here?
The goal here is, well, it's about creating one specific mirror image form, what we call an enantiomer of a molecule over the other.
Like left-handed versus right-handed molecules.
Exactly like that. And why is this so vital? Well, take pharmaceuticals, for example. Often, one enantiomer is the active drug, the one that provides the therapeutic benefit. Its mirror image might be completely inactive, or sometimes, unfortunately, it could even cause harmful side effects.
Thalidomide being the tragic example.
Precisely. So controlling this chirality, this handedness, is absolutely critical in modern chemistry, especially for medicine.
So how do chemists achieve this incredible control making just one hand?
The key lies in using pyrocatalysts. And the catalyst's handedness comes from the complex organic molecules attached to the metal, the chiral ligands. Often these are special phosphine ligands, like the very famous BINAP ligand family.
BINAP.
These chiral ligands act like tiny molecular hands. They create a chiral environment around the metal atom, guiding the incoming reactant molecule into a specific orientation, ensuring that only one mirror image product is formed preferentially.
Are these successful?
Extremely. Ruthenium complexes containing BINAP ligands have been particularly successful. They're capable of reducing a variety of double bonds with exceptional enantiomeric purity, often achieving over 95% enantiomeric excess, or EE. That means more than 95% of the product is the desired mirror image.
Wow. Does the molecule being reduced need anything special for this to work so well?
For the highest selectivity, it usually helps immensely if the reactant molecule has a functional group that can also coordinate or bind to the metal. This helps lock the reactant into a very specific orientation relative to the chiral ligands. It's like having a molecular GPS guiding the reaction.
Can you walk us through the mechanism briefly?
Sure. For example, with certain unsaturated carboxylic acids, the carboxyl group, COH, coordinates strongly with the ruthenium metal. This coordination, along with the chiral BINAP ligands, establishes a very precise geometry at the metal center. The new chiral center, the new handedness, is then set in stone during the hydrogen transfer step.
Has this been used in practice, industrially?
Oh, yes. This type of reaction has been scaled up for industrial applications. For instance, producing a key intermediate for a cholesterol-lowering drug on a multi-kilogram scale, achieving that crucial 97% EE. It's also vital in the large-scale synthesis of alpha-tocopherol, which you know as vitamin E. Making the pure biologically active form requires a process involving two successive enantioselective hydrogenations using these types of catalysts.
2 steps. That really highlights the power and necessity of these methods for complex molecules.
Absolutely. Another really important application is the enantioselective hydrogenation of alpha-amidoacrylic acids to make alpha amino acids the building blocks of proteins, but specifically making one enantiomer, which is usually the biologically relevant one.
How does that work? Any interesting mechanistic details?
Detailed studies on a rhodium catalyst used for this, called DIPAM, revealed something quite counterintuitive. The reactant molecule actually binds reversibly to the catalyst, forming 2 different complexes, 2 different ways of attaching.
Okay.
But here's the twist. The complex that's present in lower concentration, the minor isomer, actually reacts faster to give the product. And it's this kinetic preference, the faster reaction of the minor species, that ultimately determines the high enantioselectivity.
That's wild. The minor pathway wins because it's faster.
Exactly. It's a beautiful example of kinetic control. Advanced computational studies using quantum mechanics have helped confirm this. They show that the rate-determining step, the hardest step in the reaction pathway, has a lower energy barrier for this minor, faster-reacting complex. These subtle energy differences at the molecular level dictate everything.
Like finding a hidden shortcut that looks harder but gets you there quicker?
A perfect analogy. And what's truly remarkable is our ability now to fine-tune these catalysts by making subtle chemical changes to the chiral ligands, maybe adding different groups onto them. Chemists can modify the electronic environment around the metal center.
And that changes the reaction.
It changes the energy balance between those competing reaction pathways, and that can profoundly impact the enantioselectivity. We can literally design and optimize these molecular hands for specific tasks, pushing the E even higher.
Okay, but what if your alkene doesn't have a helpful coordinating group? Is enantioselective hydrogenation still possible?
That's definitely a greater challenge. Without that coordinating handle, the enantioselectivity has to rely purely on subtle steric factors, basically, the molecule shape fitting into the catalyst's chiral pocket.
Any progress there?
Yes, chemists have made progress here too. Iridium-based catalysts containing chiral oxazoline rings have been developed, and they're particularly effective for certain types of alkenes, like those with aryl groups attached.
How do they manage it?
Computational study suggests it's a combination of factors. There's steric blocking, for example, a bulky group on the oxazoline ring, physically preventing the alkene from approaching from one side. And there can also be attractive interactions, like weak van der Waals forces, between parts of the alkene and the chiral ligand, which help to guide the alkene into the correct orientation for selective hydrogen addition. It's really molecular recognition at its finest. Hashtag 1.4, partial reduction of alkenes, controlling double bond geometry.
All right, let's shift gears slightly to another precise transformation. The partial reduction of alkenes, triple bonds. What's the specific goal here?
The goal here isn't usually to reduce the triple bond all the way down to a single bond, an alkene. Instead, it's typically to convert the alkene specifically into a Z-alkene.
Z-alkene. That's the cis double bond, right? Where the groups are on the same side.
Exactly, the cis isomer. And the challenge is to do this selectively, stopping the reaction cleanly at the alkene stage, while carefully avoiding over-reduction to the alkane and avoiding formation of the E-alkene, the trans isomer.
How do you achieve that kind of control?
Well, the absolute gold standard reagent for this specific transformation is Lindlar's catalyst.
Ah, Lindlar's. Heard of that one. What is it?
It's essentially a palladium catalyst, usually supported on calcium carbonate or barium sulfate, but it's been deliberately modified or poisoned with lead acetate and often quinoline.
Poisoned? Why poison your catalyst?
It sounds counterintuitive, but the lead effectively reduces the catalyst's activity just enough. It makes it less reactive, preventing it from reducing the newly formed double bond any further.
Ah, so it's like putting a speed limiter on the reaction. It can reduce the triple bond, but it's too slow to reduce the double bond afterwards.
That's a great way to put it. It ensures the reaction stops precisely at the desired Z-alkane stage. There are other options too, like a nickel boride catalyst called P2 nickel, and some specific rhodium catalysts can also show good selectivity for this Z-alkene formation. Hashtag 1.5. Hydrogen transfer from diamide. A gentle, selective method.
Okay, now for something completely different. Hydrogen transfer from diamide. You describe this as gentle and selective.
Yes, it's a really neat method. Diamide, its chemical formula is HNNH, is actually an unstable molecule. You can't just buy a bottle of it. It's typically generated right there in the reaction flask, in situ, as you need it.
So what makes this unstable molecule so special?
Its selective power. Diamide is really good at reducing carbon double bonds, but, and this is the crucial part, it generally leaves many other easily reduced functional groups completely untouched.
Like what?
Things like nitro groups, cyano groups, even some carbonyl groups, peroxides, sulfides, groups that would be readily attacked by standard catalytic hydrogenation or strong hydride reagents. Diamide just ignores them.
Wow, that sounds incredibly useful if you have a complex molecule with lots of different groups.
Exactly. It's a massive advantage in complex syntheses where you want to selectively reduce one double bond without destroying another sensitive functional group elsewhere in the molecule.
What's the mechanism? How does it achieve this selectivity?
The mechanism behind this is quite elegant. It's believed to involve a concerted syn transfer of hydrogen.
Concerted meaning all at once. Syn meaning same side again.
Correct, on both counts. It proceeds through a non-polar cyclic transition state where both hydrogen atoms from the diamide are transferred simultaneously to the same face of the double bond. This concerted cyclic mechanism explains both the observed syn stereochemistry and its remarkably gentle nature, avoiding harsh conditions or reactive intermediates.
Does the type of double bond matter? Is it faster for some than others?
Yes, the reaction rate is influenced by strain in the alkene. Generally, more strained double bonds react faster with diamide. For instance, if you have a molecule with both a cis and a trans double bond within a medium-sized ring, the more strained trans double bond might be selectively reduced, leaving the less strained cis bond untouched.
Even more layers of control. How do you make this diamine if it's unstable?
There are several ways. A common method is the decomposition of azotic carboxylic acid, or its potassium salt. Another is the thermal decomposition of p-toluenesulfonyl hydrazide. What's interesting about that source is it leaves even highly reducible disulfide bonds completely untouched. Oxidation of hydrazine is another route.
Has diamide been used in challenging syntheses?
Oh, yes. We've seen it used in sophisticated natural product syntheses. For example, the selective reduction of a trans double bond within a large macrocyclic lactone ring, which was a crucial step in making analogs of apothalones, potent anti-cancer agents. This truly underscores its value when you're dealing with highly sensitive or structurally complex molecules where traditional hydrogenation methods might just chew up the molecule.
Okay, so far we focused heavily on carbon double and triple bonds, but you mentioned earlier that catalytic hydrogenation is broader than that. It can hit other functional groups too.
That's right. It's a versatile tool. For instance, ketones, aldehydes, and esters can all potentially be reduced to alcohols using hydrogen and a catalyst.
So they're that common.
Honestly, these reactions are often slower and sometimes less selective than alkene hydrogenations. And for most routine synthetic applications, chemists usually prefer using those specialized hydride transfer reagents, like borohydride or LiLA, for reducing carbonyls. We'll get into those in detail next.
So hydrogenation of carbonyls is possible, but maybe not the first choice usually.
Generally not the first choice unless there's a specific reason, maybe compatibility with other groups or a particular stereochemical outcome is desired. But it does provide an alternative route.
Where does catalytic hydrogenation really excel beyond, see, multiple bonds?
One area where it truly excels is the rapid and efficient reduction of nitro compounds, nitro-nitroureos, all the way down to primary amines, NH. This is a very common, reliable, and practical transformation in organic synthesis.
Okay, nitro to amine, that's a big one. Anything else?
Other nitrogen-containing groups like imines, CNs, and nitriles, CSN, can also be reduced to imines. Amides, CO linked to N, however, typically require quite extreme conditions, very high pressures and temperatures, and they're rarely reduced this way in practical lab synthesis. Hydride reagents are much better for amides.
Got it. You also mentioned something called a hydrogenolysis earlier. What's that about?
Hydrogenolysis literally means cleavage by hydrogen. It's where a functional group, typically a halogen atom or certain oxygen-containing groups, is completely removed and replaced by a hydrogen atom.
So not just reducing a group, but completely removing it.
Exactly. For halides, the reactivity order generally follows the ease of breaking the carbon-halogen bond. Iodides are easiest, then bromides, chlorides, and fluorides are very difficult. CF bonds are usually inert.
Where is this most useful?
This type of reaction is incredibly useful synthetically, especially for removing oxygen functionalities at specific positions, particularly benzylic positions right next to an aromatic ring, and allylic positions right next to a double bond.
Ah, like benzyl ethers, protecting groups.
Precisely. A great example is using hydrogenolysis, usually with palladium on carbon, PDC, to cleave benzyl ethers, BNOR. The reaction breaks the benzyl-oxygen bond, giving you back your alcohol, ROH, and generating toluene as a byproduct.
That sounds very clean.
It is. This facile cleavage makes the benzyl group an excellent protective group for alcohols and sometimes amines during a multi-step synthesis. You put it on to mask the reactive group, do other chemistry elsewhere, and then cleanly remove it at the end with simple hydrogenation. The classic carbobenzyloxy CBZ group used in peptide synthesis relies on exactly this principle for deprotection.
Okay, so hydrogenolysis is great for removing certain groups. What about anion selective reduction of carbonyls using hydrogenation? Is that feasible?
Yes, absolutely. There's been significant development in the enantioselective reduction of carbonyl groups, particularly ketones, using chiral hydrogenation catalysts. This is driven by the huge importance of chiral alcohols as building blocks.
Similar catalysts to the alkene ones?
Yeah.
Like BINAP?
Yes. Chiral-ruthenium BINAP catalysts, for example, show excellent enantioselectivity for reducing certain types of ketones, like eketoesters. And interestingly, adding a small amount of acid can sometimes accelerate these reactions, making them more practical, allowing them to run efficiently at lower hydrogen pressures and temperatures.
What about simpler ketones without that extra ester group?
For reducing simpler monofunctional ketones to chiral alcohols, Catalysts containing chiral diamine ligands have proven highly effective. These often exhibit strong selectivity for the carbonyl group, leaving carbon-carbon multiple bonds untouched if they are present elsewhere in the molecule.
Is the mechanism known for those?
Their proposed mechanism is quite fascinating and actually distinct from many other hydrogenations. It's believed that the unmean NH group of the chiral diamine ligand actively participates in the hydrogen transfer step.
So the hydrogen doesn't come directly from the metal.
Not directly to the ketone carbon, no. It seems the ketone doesn't directly contact the metal during that critical hydride transfer step. Instead, it's thought to be a concerted process involving a six-membered transition state where hydride is delivered from the ruthenium, while a proton is simultaneously transferred from the catalyst's nitrogen atom to the ketone oxygen. This intricate non-contact transfer mechanism is key to achieving the high enantiomer selectivity.
Okay, this seems like a perfect transition. You mentioned that for carbonyls, chemists often prefer hydride reagents. So let's dive into those. The group 3 hydride donor reagents, primarily boron and aluminum-based, you call these the precision tools.
I think that's fair. When it comes to reducing carbonyl compounds, aldehydes, ketones, esters, acids, and so on, these boron and aluminum hydride reagents are often your go-to choices because they offer an incredible degree of control, both in terms of which functional group reacts, chemoselectivity, and the 3D outcome, stereoselectivity.
Who are the main players here?
The two biggest players, the ones everyone learns first, are sodium borohydride, NeBH, and lithium aluminum hydride, LiLH, often just called LH.
Right. And they're quite different, aren't they?
Very different. They represent two very different levels of reactivity, which is incredibly useful. NeBH is a relatively mild reducing agent. It's great for rapidly reducing aldehydes and ketones, which are generally quite reactive carbonyls, but it's very slow, almost unreactive, with less reactive carbonyls like esters or amides under normal conditions.
It's easy to handle.
Yes, a big advantage of NeBH is its stability. It's stable enough to be used in prussidic solvents like water or alcohols like methanol or ethanol, making it very convenient and forgiving to work with in the lab.
Okay, so NeBH is the dental option. What about LiLH?
LiLH is the powerhouse, the sledgehammer, if you will. It's much, much more reactive. It readily reduces esters, carboxylic acids, nitriles, and amides, in addition to aldehydes and ketones. It basically reduces most polar functional groups containing oxygen or nitrogen.
But there's a catch.
There's definitely a catch. Because it's so reactive, LiLH is also a strong base, and it reacts violently with prototic solvents like water or alcohols. It rips a proton off them, releasing flammable hydrogen gas in the process.
Yikes. So careful handling needed.
Absolutely. It must always be used in anhydrous, meaning water-free, non-prototic solvents, typically ethers like diethyl ether or tetrahydrofuran, THF, and reactions need to be carefully quenched afterwards, usually by slowly adding water or aqueous acid at low temperature.
So what makes LiL so much more reactive than NeDH?
It comes down to a combination of factors involving both the metal cation and the hydride anion itself. First, the lithium cation, Lil, is smaller and has a higher charge density than the sodium cation, making it a stronger Lewis acid.
Lewis acid, meaning it coordinates more strongly to the carbonyl oxygen.
Exactly. It activates the carbonyl group more effectively towards attack. Second, the aluminohydride anion, ILH, is inherently a more potent hydride donor than the borohydride anion, GH. The aluminum hydrogen bond is weaker and more polarized than the boron hydrogen bond.
Makes sense. Do either of these react with regular carbon-carbon double bonds?
Generally, no. Neither NeBHR nor LiLHR reacts with simple, isolated CC double bonds. That's a very useful point of selectivity. You can often reduce a carbonyl group in the presence of a double bond using these reagents, though alpha-beta unsaturated systems are a special case we'll get to.
How do these reactions work mechanistically, the hydride transfer part?
The general mechanism involves the carbonyl group first being activated by coordinating with that metal cation, the Lewis acid part we just mentioned. Then, the hydride from the BHA, or LH-alanine, transfers nucleophilically to the partially positive carbon atom of the activated carbonyl group.
Okay, one hydride transfers. What about the others? Both reagents have 4 hydrogens.
That's right. And in principle, all 4 hydrides on the boron or aluminum can eventually be transferred, reducing multiple carbonyl molecules. What's interesting is that as each hydride is transferred, the remaining boron or aluminum species, like BHO or LH or LH, actually becomes progressively more Lewis acidic, which can influence the rate and selectivity of the subsequent hydride transfers.
Fascinating. What about reducing amides to amines with LiLH? You said that's important. Is the mechanism different?
It's a bit more complex. After the initial hydride addition to the amide carbonyl, the oxygen atom, coordinated to aluminum, becomes a good leaving group. Unlike esters, which eliminate an alkoxide, here the intermediate collapses, and eventually, after further reduction steps, the C-iodo group is fully reduced to a CH-arrow group, giving the amine. If you have primary or secondary amides with NH bonds, the strongly basic Lyell arrow often first deprotonates the nitrogen before reduction occurs. But the bottom line is, it's a very important and widely used method for synthesizing amines.
You mentioned that cation matters, LH versus NaBeOH. Are there other variations?
Oh yes. Chemists have played with the catechation to fine-tune reactivity. For example, lithium borohydride, LiBH, or zinc borohydride, ZnBHs, are both significantly more reactive than sodium borohydride, precisely because Leia and Zeno are stronger Lewis acids than Neom. They can sometimes reduce esters, which NiBH usually won't touch. This gives chemists more options to match the reagent's power to the specific task.
Any other clever modifications?
Absolutely. A particularly ingenious one is sodium cyanoborohydride, NaBeAH. Notice the cyano group NaCN replacing one hydrogen.
What does the cyano group do?
It's strongly electron withdrawing. This pulls electron density away from the boron, making the remaining BH bonds less reactive, less prone to donate hydride.
So it's a weaker reducing agent. Why is that useful?
It makes it highly selective. NeBeHCN is much more reactive towards positively charged iminium ions, or RENR, which are essentially protonated neurons, than it is towards neutral carbonyl group, like ketones or aldehydes, especially if you keep the reaction mixture at a mildly acidic pH, around 6 to 7.
So you can have a ketone and an emi in the same pot. They form an iminium ion equilibrium, and the NaCN selectively reduces only the iminium ion.
Precisely. This remarkable selectivity is the basis of reductive amination, a cornerstone transformation in organic synthesis. It allows you to directly convert a ketone or aldehyde and an amine, primary or secondary, into a secondary or tertiary am, respectively, in a single convenient step. Incredibly useful for building albumin structures.
That is clever. Are there even more specialized hydride reagents?
You bet. We have things like alkyl borohydrides. Commercially, some are known by trade names like selectrids, L-selectrid, K-selectrid. These are made by reacting trialkylobaranes with metal hydrides. The key feature is that they have bulky alkyl groups attached to the boron.
Like the bulky catalyst we discussed. What does the bulk do here?
That steric hindrance, that bulkiness, leads to significantly increased stereoselectivity. Because the region itself is large and demanding, it can only approach the molecule being reduced from the least crowded direction, leading to very specific 3D outcomes. We'll see examples later.
Okay. Any aluminum variations like that?
Yes, there are alkoxide-modified aluminum hydrides. A well-known example is sodium bis-2-methoxyethoxy aluminum hydride, often called red Ali. By replacing some of the hydrides on aluminum with alkoxide ions, you achieve a couple of things. It often increases solubility in organic solvents, even nonpolar ones like toluene. And importantly, it allows reactions to be run effectively at very low temperatures, like -70 degrees C.
And low temperature often means better control, right?
Exactly. Better control, potentially higher selectivity, especially for partial reductions, which we'll get to.
So far, these have all been based on anions like BHO or ALSO. Are the neutral hydride reagents too?
Yes, there are the neutral boron and aluminum hydrides, borane, BH, which usually exists as the dimer deborane, BH, and alane. Unlike the anionic hydrides, these are actually electron-deficient molecules. They act as electrophilic Lewis acids, meaning they want to accept electron pairs.
So they react differently.
Their reduction mechanism is thought to involve coordination to the oxygen or nitrogen of the functional group first, forming a complex. Then, hydride transfer occurs intramolecularly within that complex.
Does borane have useful selectivity?
Deborane BH has a very useful and distinct selectivity pattern. Its standout feature is that it readily reduces carboxylic acids, COOH, to primary alcohols, CHOOH, under relatively mild conditions, while typically leaving esters, debro, are completely untouched. That's a really valuable distinction.
Wow, that is selective. Acid, yes. Ester, no.
What about other groups? Nitro and cyano groups are also relatively unreactive towards deborane. Its rapid reaction with carboxylic acids is thought to proceed via formation of an acyloxyborane intermediate, which greatly enhances the carbonyl's reactivity towards further reduction by borane. It's also very effective at reducing amides to amines.
And alane? Similar.
Alane LH shares some similarities. It also readily reduces amides to amines, and crucially, it can do this selectively even in the presence of esters. Again, its electrophilic nature, its tendency to coordinate strongly with the more basic amide oxygen over the ester oxygen, drives this selectivity. It's also useful for reducing sensitive molecules like certain strained beta-lactam rings without causing them to break open, which can be a problem with LiOLARO, hashtag 3.2, partial reduction of carboxylic acid derivatives, stopping at the aldehyde.
Okay, you mentioned partial reductions. One of the classic challenges in reduction chemistry is the partial reduction of a carboxylic acid derivative, like an ester or an acid chloride, just down to the aldehyde stage without over-reducing it all the way to the primary alcohol. Why is that so tricky?
It's tricky because aldehydes themselves are generally more reactive towards hydride regions than the esters or acid chlorides they come from. So as soon as some aldehyde is formed, it wants to react again immediately with any remaining reducing agent. Getting the reaction to stop cleanly at the aldehyde stage is like trying to stop a speeding train precisely at an intermediate station rather than letting it run all the way to the terminus.
So how do chemists manage to stop the train?
They've devised several clever strategies. One common approach relies on using steric hindrance in the reducing agent. By replacing some of the hydrogens in the hydride region with bulky groups, you create a bulky hydride that is less reactive and more discerning.
Like the selectrides.
Well, a classic example for converting acid chlorides to aldehydes is lithium tri-T-butoxyaluminum hydride. The three bulky T-butoxy groups make it much less reactive than Licuro, allowing it to react with the very reactive acid chloride, but stopping before it significantly reduces the resulting aldehyde.
What about reducing esters partially? That sounds harder, since esters are less reactive than acid chlorides to begin with.
It is harder, but possible with the right reagents and conditions. Red Al, which we mentioned earlier, is fantastic here. Its excellent solubility, even at very low temperatures, like -78 degrees C, allows for highly controlled additions. You can carefully add just one equivalent of hydride at low temp, reducing the ester to an intermediate that collapses to the aldehyde only upon warming or workup.
So low temperature is key.
Low temperature and stoichiometry, yes. But perhaps the most widely used reagent specifically for the partial reduction of esters and lactones, cyclic esters, to aldehydes and lactols, cyclic hemiacetyls respectively, is disobutaluminum hydride. You probably know it as dibol or dibol H.
Yes, dibol. Heard that name a lot. How does it work?
The trick with dibol is, again, careful control of stoichiometry, using exactly one equivalent, and low temperature. At temperatures like -78 degrees C, dibol adds one hydride to the ester carbonyl, forming a relatively stable tetrahedral intermediate coordinated to aluminum. This intermediate doesn't readily collapse to the aldehyde at low temperature.
So the aldehyde isn't actually formed until you warm it up or add water.
Exactly. The aldehyde isn't liberated until you perform the hydrolytic workup, adding water or mild acid. This means the aldehyde is never actually exposed to the dibol reagent under the reaction conditions, neatly preventing overreduction to the alcohol. It's a very clever kinetic trick.
But
Be warned, if you use excess dibol or run the reaction at higher temperatures, it will reduce esters all the way to alcohols.
Very neat. Are there other ways to get aldehydes from acid derivatives?
Absolutely. A really powerful and quite general approach involves converting carboxylic acids into special amides called N-methoxy and methylamides, often known as Wagner-Meerwein.
Wagner-Meerwein. Okay, what's special about them?
When you treat a Wagner-Meerwein with a standard organometallic reagent, like a Grignard or organolithium, or even a hydride like ELA8 or dibol, the initial adduct forms a stable chelated intermediate involving the methoxy group. This chelated intermediate is resistant to further addition or reduction. It just sits there until you add aqueous acid during workup, at which point it hydrolyzes cleanly to give the ketone, or in the case of hydride reduction, the aldehyde.
So the intermediate protects itself from overreaction.
Essentially, yes. It's a fantastic example of designing a functional group specifically for controlled reactivity and preventing over-addition reduction. A very reliable way to make aldehydes or ketones from organometallics.
Can you get aldehydes from nitriles too?
Yes, you can also achieve aldehydes through the partial reduction of nitriles, RCA. Using dibol, again under controlled low temperature conditions, you can reduce the nitrile to an intermene intermediate, RCH-NH. The reaction conveniently stops there because the aluminum-imine complex is relatively unreactive towards further reduction. Then hydrolysis of the imine during workup gives the aldehyde RCHO.
So dibol is really versatile for these partial reductions.
Extremely versatile, yes. It's a cornerstone reagent for making aldehydes from esters, lactones, and nitriles. Hashtag 3.3, reduction of imines and amines to amines, tailoring imine synthesis.
Okay, let's move on to another crucial area, reducing amines and amines specifically to amines. This seems central to building molecules containing nitrogen. You mentioned tailoring amine synthesis.
Yes, because often you want to perform these reductions selectively in the presence of other functional groups. It's about choosing the right tool for the specific job to build complex nitrogen-containing structures precisely.
We already touched on reductive amination with sodium cyanoborohydride. Are there other aspects of chemoselectivity to consider when making amines?
Definitely. When you need to reduce one group while leaving another untouched, it's all about matching the reagent's reactivity. For example, we know NABH reduces aldehydes and ketones much faster than esters. So if you had a molecule with both a ketone and an ester, and you wanted to somehow convert the ketone part into an amine, maybe via an intermediate amine, NABH might be suitable because it wouldn't touch the ester.
Okay, exploiting reactivity differences. What about that selective aminium reduction again?
Right. Sodium cyanoborohydride, NaBACN, is the star player for reductive amination. Its special power is reacting rapidly with protonated imium ions, while being largely unreactive towards neutral carbonyls at that crucial pH 6-7. This allows the direct, one-pot conversion of ketones or aldehydes plus an imine into a secondary or tertiary amine product. It's just incredibly efficient.
Is it the only option for that?
Not anymore. Another very popular and often milder alternative for reductive amination is sodium triacetoxyborohydride, often abbreviated as STAB or NABH. It's become very widely used.
Stab. Okay,
Right.
how does it compare?
It's generally effective for a wide variety of aldehydes and ketones reacting with primary and secondary amines, including less reactive ones like aniline derivatives. It often gives cleaner reactions and doesn't require the careful pH control that NaBKCN sometimes needs, nor does it involve cyanide. It's even used routinely in large-scale drug syntheses in industry now, which speaks volumes about its practical utility. Zinc borohydride, ZNDH, especially when used with silica gel, is another reagent that can affect efficient reductive amination, even with sensitive alpha-beta unsaturated aldehydes or ketones. The zinc likely helps in forming the imine intermediate too.
So, plenty of options for reductive amination. What about reducing amides directly to amines? You said LiLHO works, but can be harsh.
Right, LiLHE does the job, reducing amides to amines, but it often requires heating, and as we know, it nukes almost everything else. This limits its selectivity if other sensitive functional groups are present.
So what are the more selective alternatives for amide for reduction?
This is where deborane BH really shines. We mentioned earlier it's great for reducing carboxylic acids, but leaves esters alone. It's also excellent for reducing tertiary and secondary amides to amines. It's less effective for primary amides sometimes.
Why is it good for amides?
Again, it's about its electrophilicity. Borane complexes preferentially with the more electron-rich amide carbonyl oxygen compared to, say, an ester carbonyl oxygen. This coordination activates the amide towards reduction.
And the selectivity.
Critically, deborane allows the selective reduction of amides even in the presence of esters and nitro groups, which LiLH would likely reduce as well. This is a huge advantage. Alane, as we also noted, is similarly useful for selectively reducing amides to amines in the presence of ester groups, thanks to its electrophilicity.
Are there other tricks for amide reduction?
Yes, sometimes chemists activate the amide first to make it more reactive towards milder hydride reagents. For example, you can convert the amide oxygen into an O-alkyl group, creating a positively charged species that's much more easily reduced. Or you can make related reactive intermediates. This allows reduction under milder conditions than direct LiLHO or borane treatment, #tag 3.4, reduction of unsaturated carbonyl compounds, 1^2 versus 1^4 reduction.
Okay, let's tackle a classic challenge you hinted at earlier. Reducing apo-unsaturated carbonyl compounds, often called enones or enols. What's the dilemma here?
The dilemma arises because these molecules have two potential electrophilic sites where a hydride nucleophile could attack. There's the carbonyl carbon itself, position 2 if you number from the oxygen, and there's the beta carbon of the double bond, position 4.
Right, the double bond is conjugated with the carbonyl, so hydride can add to either place.
Exactly. Attack at the carbonyl carbon is called 1^2 reduction. This leads to an allylic alcohol. The double bond remains untouched, but the carbonyl becomes an alcohol.
Okay, and the other option?
Attack at the beta carbon, position 4, is called 1^4 reduction or conjugate reduction. This initially forms an NLA, the anion of the saturated ketone or aldehyde. This enolate can then be protonated to give the saturated ketone or sometimes, depending on the conditions, it might get reduced further at the carbonyl to give the saturated alcohol.
So you could get an allylic alcohol, a saturated ketone, or even a saturated alcohol. That sounds messy if you want just one thing.
It can be. Standard reagents like NAPH and LyLH often give mixtures of 1,4,2 and 1,4 reduction products, sometimes favoring one over the other, but often without perfect control. NAPH, for instance, sometimes leads to more of the fully saturated alcohol product.
So the goal is selective reduction. How do you achieve that? Can you force it one way or the other?
Yes. Fortunately, chemists have developed specific reagents and conditions that strongly favor either 1,4 or 1,4 reduction.
Okay, how do you get exclusive 1,2 reduction, just the allylic alcohol?
A very effective method is using Lusch's reagent. This is simply NaBH used in combination with a lanthanide salt, typically cerium-3, chloride, C-chloros, usually in methanol.
Cerium chloride, what does that do?
The cerium ion is a strong Lewis acid that coordinates preferentially to the hard oxygen atom of the carbonyl group. This strongly activates the carbonyl towards 1-2 attack by the bore hydride while suppressing the competing 1-4 addition pathway. It dramatically shifts the selectivity towards the allylic alcohol. Other reagents like Diebel at low temperature or hindered boranes like 9-BBN also often give predominantly 1-2 reduction.
Clever. Okay, what about the other way? How do you get exclusive 1,4 reduction to the saturated ketone?
Well, catalytic hydrogenation, like HERC, typically saturates the double bond first, so that's one way to get the saturated ketone. But using hydride chemistry, the key is often to involve copper. Reagents prepared from hydride-reducing agents like LyLH or silanes and copper salts, often referred to generically as copper hydrides, though their exact structure is complex, are very effective for 1,4 reduction.
Copper hydrides.
Yeah.
How do they work?
They are thought to operate via a conjugate addition mechanism, where the hydride delivered by copper adds specifically to the beta position, position 4, generating the enolate of the saturated ketone. This method works well for enones, and similar regions can achieve 1/4 reduction of unsaturated esters and nitriles too.
Any other methods for 1,4,4?
Yes, there are other specialized systems, for instance, using cobalt catalysts with Diebel, or using Wilkinson's catalyst, the rhodium one, but with triethylsilane as the hydride source instead of H0 gas. That latter method actually gives you the silyl-enol ether of the saturated ketone, which can be useful itself or easily hydrolyzed. There's also a neat trick where enol ethers of beta dicarbonyl compounds can be reduced to alpha-beta unsaturated ketones using Li followed by hydrolysis, a useful way to synthesize substituted cyclohexanones. Hashtag tag 3.5, stereoselectivity of hydride reduction, controlling the molecular shape.
All right, we've talked about what gets reduced and where reduction happens. Now let's dive deeper into the how in 3D space. Stereoselectivity of hydride reduction. This sounds like where the real art of synthesis comes in.
It really is. Directing hydride additions to create very specific stereoisomers, specific 3D arrangements of atoms, is absolutely crucial for building complex molecules, especially things like natural products or pharmaceuticals, where the exact shape determines biological activity.
What factors control this 3D outcome?
It generally comes down to a combination of steric effects, essentially. The physical bulk of different parts of the molecule and the reagent, and sometimes more subtle stereoelectronic effects, which involve how molecular orbitals interact during the reaction.
Let's start with cyclic ketones, like cyclohexanones. They're often used as models, right?
Exactly. Cyclohexanones are great systems for studying stereoselectivity. One major factor is steric approach control. If you use a really bulky hydride donor like L-selectrid, which has bulky sec-butyl groups, it simply prefers to attack the carbonyl carbon from the less sterically hindered face.
Which face is that usually on a cyclohexanone?
That's typically the equatorial face. Attack from the equatorial direction leads to the formation of the axial alcohol. So bulky reagents tend to give axial alcohols. Imagine trying to squeeze a big reagent past the hydrogens sticking up or down, axial, on the ring. It's easier to come in from the side, equatorial.
Okay, bulky reagent, equatorial attack, axial alcohol. What about less bulky reagents like NABH or LyLH?
With smaller, less hindered donors like NABH or LyLH, you often get the opposite result. They tend to give predominantly the equatorial alcohol, which is usually the thermodynamically more stable product.
Why the switch? If equatorial attack is less hindered, why don't they do that too?
It's a bit more complex and still debated, but a leading explanation involves torsional strain in the transition state. As the hydride approaches axially, the carbonyl oxygen has to bend down towards the equatorial position. This path is thought to minimize unfavorable twisting interactions, torsional strain, with the adjacent equatorial CH bonds compared to the alternative equatorial approach. There are also proposed orbital arguments suggesting the LMO, lowest unoccupied molecular orbital of the carbonyl, might be slightly more accessible from the axial face for small nucleophiles. But torsional strain is a common explanation.
Interesting. So small reagents might prefer axial attack, leading to the equatorial alcohol. You mentioned Luch's reagent Nabiacio earlier for 1/C reduction. Does the cerium affect stereochemistry too?
It can. Sometimes adding Cyclus can actually reverse the stereoselectivity observed with NaBH alone, often favoring the more thermodynamically stable alcohol product. The exact mechanism is complex and might involve formation of different active reducing species.
Okay, that covers cyclic systems. What about acyclic ketones, straight chain ones, especially if they have a chiral center nearby? How do you predict the outcome there?
For acyclic aldehydes and ketones with an adjacent chiral center, the stereoselectivity can often be successfully predicted using the Felkenan model. It's a conformational model that helps visualize the preferred arrangement during attack.
Felkenan. How does it work?
The model suggests that the molecule adopts a specific conformation before the hydride attacks. The largest substituent, L, on the alpha carbon, the carbon next to the carbonyl, orients itself perpendicular to the plane of the carbonyl group. This minimizes steric clash with the incoming nucleophile and the carbonyl oxygen.
Largest group perpendicular. Okay, then where does the hydride come from?
The hydride then attacks the carbonyl carbon from the face opposite the largest group, L, usually following a trajectory slightly offset towards the smallest group on the alpha carbon, minimizing steric interactions with both the large L and medium-sized M groups.
Is it purely steric?
Not entirely. Beyond just simple steric blocking, there's also thought to be a favorable stereoelectronic effect. The perpendicular arrangement of the largest, often most electronegative group, helps stabilize the transition state by allowing better overlap between the incoming nucleophile's orbital and the carbonyl's LMO, the accepting orbital.
Can you give an example?
Sure. Studies on alpha-substituted phenylketones show a stereoselectivity order where unsaturated groups like alkyl or vinyl, CHCS, act as the largest group electronically, preferring that perpendicular position for optimal orbital interaction, even if they aren't physically the biggest.
Wow. And can things further away influence this? Remote effects?
Yes. Sometimes remote steric factors, bulky groups several atoms away from the reaction site, can also influence the stereochemical outcome, especially when you use very bulky reducing agents. We see this in complex molecule synthesis, like prostaglandin intermediates, where a remote group directs the approach of a bulky borohydride. It shows how the molecule's overall 3D shape can subtly guide the reaction.
This is getting intricate. Is there another guiding principle besides just sterics and Felkenan?
Yes, a very powerful one, chelation control.
Chelation.
Yeah.
Like forming a ring with a metal.
Exactly.
Yeah.
This happens when you have a nearby functional group with atoms that can donate electrons, like oxygen or nitrogen from an OH or R or NR group, positioned correctly relative to the carbonyl. This donor group can coordinate or chelate with the metal cation, like Leo, Mgru, Xenohu, or even boron that's associated with the hydride reagent.
What does that chelation do?
It forms a temporary rigid chelated ring structure involving the metal, the carbonyl oxygen, and the donor atom. This locks the molecule into a specific conformation. Once that rigid chelate is formed, the hydride then usually delivers from the less sterically hindered face of this specific conformation, overriding the normal Felkenan prediction.
Can you give an example?
A classic case is the reduction of alpha-hydroxy or alpha-alkoxy ketones. Reagents like zinc borohydride or even Lyl-H often reduce these to give predominantly the anti-142 diol or amino alcohol. This happens because the alpha oxygen chelates to the metal, setting up a 5-membered ring, and a hydride delivers anti to the alpha substituent. The selectivity often increases with the bulk of the groups involved.
What about groups further away, like gamma-hydroxyketones?
Yes. Gamma-hydroxyketones can also be controlled by chelation, often leading to syn-1,3 diols. Boron reagents are particularly good for this. There's a fantastic procedure using diethylmethoxyboron and NaBH. The boron reagent forms a 6-membered chelate in situ, and the subsequent NaBH reduction delivers hydride intramolecularly, giving predominantly the syn-1,3 diol with a very high selectivity.
Was that the Lascaux example you mentioned?
That's the one. The syn-1,1,3 diol reduction using boron chelation control was a key step in synthesizing the cholesterol-lowering drug, Lascaux fluvastatin. a perfect real-world application. Other metal combinations like Li-Li-Allo or using Tycal as the chelating agent with gamma-methoxy ketones also work.
So chelation is a powerful way to dictate stereochemistry by temporarily locking the conformation.
Incredibly powerful. It's used to control reductions near epoxides, sulfoxides. If you have a Lewis basic group positioned correctly, you can often use chelation to direct the hydride delivery with high precision. Hashtag 3.6. An enantioselective reduction of carbonyl compounds, creating single enantiomers.
Okay, we've seen how to control stereochemistry in general. But what about the ultimate goal, enantioselective reduction? Taking an acryl ketone and turning it into predominantly one specific mirror image, one enantiomer of the alcohol? This sounds like the holy grail.
It is a major goal in modern organic synthesis, absolutely. Creating single enantiomers of chiral alcohols is incredibly important, especially for pharmaceuticals and biologically active molecules where, as we discussed, only one enantiomer usually has the desired effect.
How is this achieved with hydride reagents?
One major approach involves using chiral borane reagents. These are typically derived from chiral alkenes, like alpha pine from pine trees. You can make chiral alkyl boranes from these and then convert them into chiral alkyl hydrides.
Like chiral versions of the selectrides.
Sort of, yes. Examples include reagents nicknamed alpine hydride or NB enantioride. There are also related chiral chloroboranes like IPCARO-BCl, desapinocamphylboron chloride derived from alpha pine. These have proven to be highly effective for the enantioselective reduction of various types of ketones, particularly aryl ketones and hindered dialkyl ketones.
Are they practical? Used on large scale?
They can be. For instance, one of these chiral chloroborane reagents was used in the multi-kilogram scale synthesis of a Merck leukotriene antagonist drug candidate, L699392, achieving an outstanding 99.5% antiomeric excess. That's astonishing precision for such a large-scale chemical process.
How do they work? What's the mechanism for the chirality transfer?
These chiral borane and borohydride reagents are believed to react through highly organized cyclic transition states. The chirality embedded in the region is effectively transferred to the ketone during the hydride delivery step, dictating which face of the carbonyl is attacked. The reaction often regenerates the chiral starting material, like the pine, making it potentially catalytic in the chiral auxiliary, though often stoichiometric amounts are used.
Stoichiometric chiral reagents can be expensive, though. Is there a catalytic way to do this enantioselective reduction with hydrides?
Yes, and this has been a huge area of development. The most significant breakthrough came with the development of chiral oxyzborolidine catalysts, often referred to as CBS catalysts, named after Corey, Bakshi, and Shibata.
CBS catalysts. Okay, what are they?
They are derived from chiral amino alcohols, most commonly from the readily available amino acid proline. These oxyzborolidines are incredibly powerful chiral catalysts for the reduction of ketones using simple borane, BH, as the stoichiometric reductant.
So you only need a small amount of the extensive chiral part.
Exactly. You typically only need a catalytic amount, maybe 5 to 20 mol% of the CBS catalyst. This, combined with the inexpensive borane, can reduce a wide range of ketones to chiral alcohols with very high enantioselectivity, often exceeding 95% EE.
That sounds incredibly useful. How does the catalyst work its magic?
The mechanism is quite elegant. The active reductant is believed to be an adduct formed between the borane, BH as the nitrogen atom of the oxyzborolidine ring. The ketone then coordinates to the boron atom within this complex. The rigid chiral structure of the oxyzborolidine, often featuring a strategically placed phenyl group, dictates the orientation of the ketone.
So it positions the ketone just right.
Precisely. It forces the ketone to adopt a specific conformation, usually in a chair-like transition state, where one face is effectively shielded by the catalyst structure. Hydride is then delivered internally from the coordinated BH group to the exposed face of the ketone. Computational studies support this model, showing why one approach, termed exo, is strongly preferred over the alternative, endo, leading to the high observed enantioselectivity. The catalyst essentially acts as a highly selective molecular vice, holding the ketone precisely for hydride delivery.
Have CBS catalysts found wide use?
Immensely broad applications. They've been used in countless syntheses, from complex drug candidates and prostaglandin precursors to reducing simple cyclic and acyclic ketones, and even for reducing aromatic ketones on large scale in drug development programs. They are truly versatile and indispensable tools in modern organic synthesis, offering unparalleled enantio control for ketone reduction with borane.
What about enantioselective 1-4 reduction of enants? Is that possible catalytically?
Yes, that's another important area. Copper catalysts paired with chiral ligands, particularly binap and related diphosphenes, have been developed for the highly enantioselective conjugate reduction, 1,4 reduction of enones. These systems typically use silicon hydride donors like polymethylhydrosiloxane, PMHS, or diphenylsilane as the stoichiometric hydride source.
So chiral copper catalysis for 1,4 reduction.
Exactly. They can achieve excellent enantiomeric excesses, often over 90% Ni, and this powerful method can even be integrated into tandem reaction sequences, allowing for further synthetic manipulation after the precise chiral 1,4 reduction step. Hashtag 3.7, reduction of other functional groups by hydride donors.
We've focused heavily on carbonyls, but you mentioned hydrides can reduce other things too, like replacing halogens.
Yes, hydride donors, both aluminum and boron-based, can be used for the replacement of halogens, I, Br, Cl, and sulfonate-leaving groups, like tosylates or mesylates, with hydrogen. Essentially, Rx becomes Rh.
Which reagents are best for this?
Lithium trialkylbor hydrides, like LEAP-BH, superhydride, are particularly reactive and effective for this transformation, especially when run in polar apotic solvents like DMSO or HMPA. Liquid can also work, but sometimes requires harsher conditions.
How does this reaction happen? Is it like an SN2 reaction?
For simple primary alkyl halides, it likely proceeds via a direct SN2 displacement mechanism, where the hydride acts as a nucleophile attacking carbon and kicking out the halide. However, for substrates that can't easily undergo SN2, like aryl halides, vinyl halides, or bridgehead halides, or when stereochemistry is lost, the evidence points towards radical intermediates.
Radicals again. How would that work?
It's thought that the hydride reagent might first transfer a single electron to the alkyl halide, forming a radical anion. This radical anion then rapidly fragments, losing the halide ion to give an alkyl radical. This alkyl radical then abstracts a hydrogen atom from another source, perhaps the solvent or another hydride molecule, to give the final RH product.
How do chemists test for these radical intermediates?
A common trick is to use substrates containing a 5-hexanyl group. If a radical forms on that chain, it has a known tendency to rapidly cyclase, forming a 5-membered ring, a cyclopentyl methyl radical. Seeing the cyclase product is strong evidence for a radical pathway. And indeed, reductions of more hindered alkyl halides with these reagents often show this cyclization. Transition metal impurities, like copper, can also sometimes catalyze these reductions, possibly via radical pathways too.
So what's the main synthetic value of this reduction?
Primarily, it's used as a way to reductively remove a hydroxyl group. You first convert the alcohol, alcohol-H, which is a poor leaving group, into a better leaving group like a tosylate, OTs, or sometimes a halide, and then you treat it with a strong hydride reagent like lyol-H or lyose-BH to replace that group with hydrogen. It's a standard method for deoxygenation.
Okay. What about epoxides? Can hydrides open those?
Yes. Epoxides, 3-membered rings containing oxygen, are readily opened by nucleophilic attack with hydrides, typically lyol-H, to form alcohols. Attack usually occurs at the less sterically hindered carbon atom of the epoxide.
Is there stereochemistry to consider?
Yes. For epoxides derived from cyclic systems like cyclohexanes, you often observe preferential axial approach of the hydride, leading to the formation of an equatorial alcohol after ring opening. For epoxides that are particularly unreactive or prone to rearrangement, lithium triethylborohydride, LiETS-BH, is often found to be a superior reagent, giving cleaner reactions.
And finally, you mentioned lyol-H and alkanes earlier.
Right. While partial hydrogenation gives cis-alkanes, lyol-H generally reduces internal alkynes to give E-alkanes, the trans double bond isomer. This is synthetically very useful because it provides the complementary stereochemical outcome to catalytic hydrogenation.
So you can choose cis or trans depending on the region. Why does lyol-H give trans?
The mechanism is thought to involve addition of hydride to one carbon and the aluminum coordinating to the other, followed by protonolysis, leading to the more stable transgeometry. What's particularly interesting is that a nearby hydroxyl group, like in a propergylic alcohol where the OH is next to the triple bond, significantly accelerates this reduction.
Why would an OH group speed it up?
It's believed that the hydroxyl group first coordinates to the aluminum of the lyol-H. This sets up a situation where the hydride can be delivered intramolecularly via a cyclic transition state to the alkyne. This intramolecular delivery is much faster than intermolecular attack. Using deuterium labeled lyl-D confirms this, showing deuterium incorporation consistent with this internal delivery. This effect can be further enhanced by using mixtures of lyl-H and sodium ethoxide.
Okay, we've covered the workhorses from Group 3. Now let's explore some more specialized tools. Group 4V hydride donors, focusing first on silicon. Can silicon really donate a hydride?
Yes, the silicon-hydrogen bond, SH, in silanes can act as a hydride donor, but usually under specific conditions, often involving activation by strong acids or Lewis acids. It typically donates hydride to positively charged carbon species, carbocations.
So how is this used synthetically?
One application is the reduction of alcohols that can easily ionize to form stable carbocations in strong acids, like trifluoroacetic acid, TFA. In the presence of a silane, like trifilsilane, these carbocations readily accept a hydride from the silane, resulting in the formation of the corresponding hydrocarbon, RH.
What about carbonyls? Can silanes reduce them?
Aromatic aldehydes and ketones can be reduced all the way down to the corresponding alkyl aromatics, RCHR, using silanes in the presence of strong Lewis acids, like titanium tetrachloride, PuYul, or boron trifluoride. BFA, the reaction likely proceeds via formation of a benzylic carbocation intermediate, which is then trapped by hydride transfer from the silane. This method can even be used to prepare alpha-aryl amino acids.
Can you combine reactions, like forming a CC bond and reducing in one go?
Sometimes, yes. For example, certain indium chloride and chlorosilane combinations can achieve both Friedel-Crafts alkylation, adding an alkyl group to an aromatic ring, and the subsequent reduction of the resulting ketone or alcohol in a single reaction pot. Very efficient.
What about other silane reactions?
Silanes are involved in various reductive condensation reactions. For example, silyl ethers can react with carbonyl compounds in the presence of catalysts like TMSOTF or bismuth bromide to form ethers, likely involving hydride transfer from the silane at some stage.
Can silanes reduce ketones just to the alcohol stage or the silly ether?
Yes. For instance, using a specific Lewis acid catalyst, perfluorotriphenylborane, ketones can be reduced by silanes to their corresponding silly ethers. Interestingly, mechanistic studies suggest the hydride isn't delivered directly from the silane here, but rather from a borohydride anion that's formed after the silane interacts with the boron catalyst complex, a subtle but important distinction.
And antioselective versions.
Definitely. Copper catalyzed systems using tyrylphosphine ligands, like those biphenyl diphosphines, and silicon hydride donors, like PMHS or diphenylsilane, have emerged as powerful methods for the enantioselective reduction of ketones to chiral alcohols after hydrolysis of the intermediate silly ether, often achieving very high enantiomeric excesses, hashtag 4.2, hydride transfer from carbon, the classic equilibriate.
Okay, silicon hydrides are interesting. But what about hydride transfer from carbon itself? You mentioned this is rare, but possible.
That's right. The carbon-hydrogen CH bond is generally very strong and nonpolar, so it doesn't usually act as a hydride donor. However, under specific conditions, particularly those involving favorable cyclic transition states, it absolutely can transfer a hydride. This leads us to some classic named reactions.
Such as?
The most famous is undoubtedly the Meerwein-Pondorf-Verley MPV reduction.
MPV, what does it do?
In the MPV reduction, an aluminum alkoxide catalyst, often aluminum isopropoxide, facilitates the transfer of a hydride from a secondary alcohol, typically isopropanol, which acts as the reductant, to a ketone or aldehyde, which gets reduced.
So you reduce a ketone using another alcohol.
Exactly. Isopropanol gets oxidized to acetone in the process. It's an equilibrium reaction, meaning it can go both ways. To drive the reduction forward, you usually need to remove the acetone byproduct as it forms, often by distillation.
And the reverse reaction has a name too, right?
Yes, the reverse reaction, where you use a large excess of a ketone, like acetone, to oxidize an alcohol, is called the Oppenauer oxidation. It's the same equilibrium, just pushed in the opposite direction.
What's the mechanism of the MPV reduction?
It's believed to involve a cyclic, six-membered transition state where both the alcohol, isopropanol, and the ketone coordinate to the aluminum atom of the catalyst. This brings the CH bond of the isopropanol close to the carbonyl carbon, allowing for the intramolecular transfer of hydride. Hydride usually donates to the less sterically hindered face of the carbonyl group.
Can this be made enantioselective?
Yes, considerable effort has gone into developing enantioselective MPV reductions using chiral catalysts, such as aluminum complexes derived from chiral ligands like binol, or other specially designed chiral aluminum or zirconium catalysts. These can achieve good enantioselectivity in reducing ketones to chiral alcohols.
Are there other examples of CH hydride transfer?
Yes, certain lanthanide alkoxides, like samarium alkoxides, can also catalyze hydride exchange between alcohols and ketones, again often using isopropanol as the hydride source. These reactions, like MPV, are often thermodynamically controlled, meaning they tend to favor the formation of the more stable stereoisomer of the alcohol product. Some iridium catalysts also achieve similar reductions using isopropanol.
Any other common CH hydride donors?
One very important one is formic acid, HCOH.
Formic acid, how does that work?
Formic acid can act as a hydrogen or hydride donor in certain reactions, with the thermodynamic driving force being the formation of stable carbon dioxide, CO gas. A classic and very useful application of this is the Eschweiler-Clark reductive methylation.
Eschweiler-Clark, what does that do?
If you heat a primary or secondary amine with an excess of formaldehyde and formic acid, the abramine gets completely methylated to form the corresponding tertiary amine.
How does formic acid do the reduction part?
The amine first reacts with formaldehyde to form an iminium ion intermediate. This iminium ion is then reduced by hydride transfer from the formate anion, derived from formic acid, which simultaneously decomposes to co-areo. It's a remarkably clean, efficient, and often high-yielding method for putting methyl groups onto amines. Our next major category takes us into a different mechanistic world, reduction reactions involving hydrogen atom donors. These reactions typically proceed not via ions or concerted steps, but through highly reactive free radical intermediates and often involve chain mechanisms.
Free radicals.
Yeah.
Species with unpaired electrons and chain mechanisms like we saw with polymerization.
Exactly. A tiny initial event initiation can trigger a repeating cycle, propagation, that leads to a large amount of product formation before the chain eventually stops and termination.
What's the most prominent example of this type of reduction?
By far the most historically prominent example is triambutylstannone, often written as BULES SNH or tributyl hydride. It's particularly famous for its ability to reductively replace halogens, especially boron, and some other groups with hydrogen. RX becomes RH.
Okay, tributyltin hydride. How does the radical chain mechanism work for dehalogenation?
It typically starts with a separate radical initiator, like AIBN, isobutysobutyrinyl, which decomposes upon heating or UV light exposure to generate a small amount of initiating radicals. These radicals then react with BURNH to generate the key tributyltin radical.
So the initiator makes the tin radical. What happens next?
This Puelzen radical is the crucial chain carrier. In the first propagation step, the tin radical attacks the alkyl halide, RX, abstracting the halogen atom. This generates an alkyl radical and tributyltin halide, BUTLNX, as a byproduct.
Now we have the alkyl radical. How does it become RH?
In the second propagation step, this alkyl radical abstracts a hydrogen atom from another molecule of butyl radical. This forms the desired product, RH, and, crucially, regenerates the tributyltin radical.
And that regenerated tin radical can then go back and react with another molecule of alkyl halide. The chain continues.
Exactly. The chain propagates until radicals are consumed by termination steps. The reactivity order for the halogen abstraction step generally follows the C-ax bond strength. Alkyl iodides react fastest, then bromides, then chlorides. Fluorides are usually unreactive.
Can this reaction be selective if you have multiple halogens?
Yes, selective dehalogenation of polyhalogenated compounds is often possible by controlling the reaction conditions or stoichiometry, exploiting those reactivity differences. The stereochemistry can also be interesting. Abstraction often occurs from the more sterically accessible face of the intermediate radical. Some radicals, like cyclopropyl radicals, can even retain their configuration.
Tributyl tin hydride sounds effective, but I've heard tin compounds can be problematic, toxic, and hard to remove completely.
That's absolutely true. The toxicity of organotin compounds and the difficulty in separating tin byproducts from the desired organic product are significant drawbacks. This has led chemists to develop catalytic procedures.
How does a catalytic tin hydride reaction work?
You use only a small catalytic amount of BuSNH, along with a stoichiometric amount of a different, cheaper, and easier to remove reducing agent, like sodium borohydride, NaBH, or sodium cyanoborohydride. The NaBH continuously regenerates the BuSNH from the BuSNX byproduct formed in the cycle. This greatly simplifies product purification.
Much better. Are there other hydrogen atom donors besides tin hydride?
Yes, partly due to the issues with tin, alternatives have been sought. For instance, hypophosphorus acid and its salts have been used as hydrogen atom donors, particularly for the dehalogenation of sensitive molecules like nucleosides, dNRNA building blocks.
Okay. What about removing oxygen using radicals? Is that possible?
Yes. A very important radical-based method for reductive deoxygenation of alcohols is the Barton-McCombie reaction.
Barton-McCombie, how does that work?
The first step is to convert the alcohol, AH, which doesn't readily undergo radical reactions, into a thiocarbonyl derivative. Common ones include thione-carbonates or xanthates. These have a CS double bond.
So you turn the alcohol into a sulfur-containing version first. Then what?
Then you treat this thiocarbonyl derivative with BUS-SNH and a radical initiator. The tin radical adds to the CS double bond. The resulting intermediate then fragments, breaking the original CO bond and generating an alkyl radical R corresponding to the alcohol backbone.
Ah, so the sulfur group acts as a handle to generate the radical on the carbon you want deoxygenated.
Precisely. This alkyl radical then abstracts a hydrogen atom from BUSNH, giving the deoxygenated product, RH, and regenerating the BUS radical to continue the chain. It's a very clever and widely used method, especially for secondary alcohols, though it can be adapted for primary ones too.
Are there non-tin alternatives for Barton-McCombie too?
Yes, absolutely. Because of the desire to avoid tin, other hydrogen atom donors are now frequently used for this reaction and other radical reductions. Popular alternatives include silicon-based hydrides like trimethylsilane, TMS, AREH, or diphenylsilane, sexy Ariero. These are often used with different initiation systems like trialkyl boron oxygen mixtures or peroxides, but they operate via similar radical chain mechanisms, offering cleaner and safer routes for these important transformations.
Okay, we've covered catalytic hydrogenation, hydride donors, and radical reactions. Our final section deals with dissolving metal reductions. This sounds dramatic. Electron powerhouses.
It's a fitting description. In these reactions, an organic reactant accepts one or more electrons directly from a metal surface. The metals used are typically highly electropositive, meaning they give up electrons easily, usually alkali metals like lithium Li or sodium Nis, often dissolved in liquid ammonia, or sometimes other metals like zinc, Zn.
So the metal just gives electrons to the organic molecule. What happens then?
When the organic molecule accepts an electron, it forms a radical anion, a species that has both a negative charge and an unpaired electron, a radical. The subsequent fate of these highly reactive radical anion intermediates dictates the overall outcome of the reaction.
What are the possible outcomes?
There are three main possibilities depending on the substrate and the reaction conditions. 1. Net addition of hydrogen, often involving protonation steps. 2. Reductive removal of a functional group where a group is cleaved off and replaced by hydrogen. 3. Formation of new carbon-carbon bonds through the coupling of two radical intermediates, what we call reductive coupling. Hashtag 6.1, addition of hydrogen. Hashtag 6.1.1, reduction of ketones and enones.
Okay, let's look at the first outcome. Net addition of hydrogen. How does this apply to ketones?
Historically, the reduction of simple ketones to alcohols was often done using sodium or potassium metal in alcohols or liquid ammonia. The reaction starts with that single electron transfer from the metal to the ketone carbonyl group, forming the initial kettle radical anion.
Kettle radical. Okay, what happens to it?
This kettle intermediate is highly reactive. In proton-donating solvents like alcohols or ammonia containing alcohol, it typically gets protonated quickly on the oxygen. Then it can accept a second electron from the metal to form a dianion, which gets protonated again, or the initially formed radical might demerize or disproportionate. But in protic solvents, the pathway usually leads to the corresponding alcohol.
Is this method still used much for simple ketone reduction? Hydrides seem easier.
Not so much for simple ketones anymore. Hydride reagents are generally more convenient and selective. However, dissolving metal reduction is still extremely important for unsaturated carbonyl compounds, emphysema.
Ah, the 1,4 reduction candidates again. What happens here with dissolving metals?
Using lithium or sodium dissolved in liquid ammonia, usually with an alcohol like ethanol or T-butanol added as a proton source, you can achieve very clean 1-enviro reduction of emergence. The product is the enolate of the corresponding saturated ketone.
The enolate, not the ketone itself.
Yes, the reaction generates the stable enolate anion. This is synthetically very significant because it's one of the best and most reliable ways to generate a specific ketone enolate regioselectively.
And why is generating a specific enolate useful?
Enolates are powerful nucleophiles used to form new carbon-carbon bonds. If you perform the dissolving metal reduction carefully, using only one equivalent of the proton donor, the alcohol, the enolate remains in solution after the reduction. You can then immediately add an alkyl halide or another electrophile to perform a tandem alkylation reaction in the same pot. This gives you incredible control over building up molecular complexity.
So reduce the double bond and then immediately add a new group next to the carbonyl. Very efficient. What about stereochemistry if you form a new chiral center?
The stereochemistry of the protonation step that forms the saturated ketone if you quench the enolate is often controlled by stereoelectronic factors. For example, in reducing bicyclic systems like octalones, the new ring junction formed usually ends up being the thermodynamically more stable trans isomer. This is thought to result from protonation occurring perpendicular to the plane of the intermediate enolate system, favoring approach to the most stable conformation from its least hindered side. Hashtag 6.1.2. Dissolving metal reduction of aromatic compounds and alkynes, Birch reduction and beyond.
Okay, dissolving metals are great for enun reduction and enolate generation. What about reducing aromatic rings? That sounds difficult. They're usually very stable.
It is difficult, but dissolving metal reduction provides the most general and synthetically powerful method for the partial reduction of aromatic rings. This specific reaction is famously known as the Birch reduction.
Well, Birch reduction, what are the typical conditions?
Typically, it involves using lithium or sodium dissolved in liquid ammonia, which is a liquid below net 33 degrees. An alcohol, like ethanol or T-butanol, is usually added as a controlled proton source.
Liquid ammonia sounds cold. How does the Birch reduction work mechanistically?
It involves two successive cycles of single electron transfer from the metal, followed by protonation by the alcohol. The aromatic ring accepts an electron to form a radical anion. This gets protonated. The resulting radical accepts a second electron to form a carbanion, which gets protonated again.
Why does it stop at partial reduction? Why not reduce all the double bonds?
That's the beauty of it. The product is typically a 1,4,4 dihydroderivative, meaning it still has two isolated non-conjugated double bonds. These isolated double bonds are much less easily reduced by dissolving metals than the original conjugated aromatic ring. So the reaction conveniently and selectively stops at this partially reduced stage.
Does it matter what groups are already on the aromatic ring? Substituent effects?
Yes, substituents significantly influence where the reduction occurs and where the protons add. Electron-releasing groups, like alkyl or alkoxy-methoxy groups, typically direct the reduction to give the 2005 dihydroderivative, where the double bonds don't involve the carbon bearing the substituent. Protonation usually occurs ortho and meta to the releasing group. Electron-withdrawing groups, like carboxylates or esters, usually direct reduction to give the 1,5 dihydroderivative, where the substituent is attached to one of the remaining double bonds. Protonation typically occurs ipso at the carbon bearing the substituent and para to the withdrawing group.
So you can predict the outcome based on the substituents. Why is the Birch reduction so useful synthetically?
It's incredibly useful for accessing non-aromatic cyclic structures. For instance, the Birch reduction of methoxy-substituted aromatic rings, anisols, is a cornerstone method for synthesizing cyclohexanones. The initial product is an enol ether, which is easily hydrolyzed with acid to reveal the ketone functional group within a six-membered ring containing one double bond.
Ah, a way to turn flat aromatic rings into useful 3D cyclic ketones. Can you do tandem reactions here too, like with the enun reduction?
Yes. The anionic intermediates formed during the Birch reduction, the carbanion formed after the second electron transfer but before the final protonation, can be trapped by adding electrophiles, like alkyl halides, directly to the reaction mixture before the final proton quench. This allows for tandem alkylation, adding new carbon groups regioselectively onto the reduced ring system, greatly expanding the synthetic possibilities.
Very powerful. What about reducing alkanes with dissolving metals? We saw LHA gives transalkanes.
Dissolving metals also reduce alkynes, and interestingly, they also predominantly give the E-alkene the trans isomer. Common conditions include sodium in liquid ammonia, or sometimes lithium in low molecular weight amines, or sodium in HMPA with T-butanol.
So another reliable way to get transalkanes, complementing Lindlar's catalyst for cisalkanes.
Exactly. The mechanism is again thought to involve successive electron transfer and protonation steps, leading preferentially to the thermodynamically more stable transalkynyl intermediate product. Hashtag 6.2, reductive removal of functional groups.
Okay, besides adding hydrogen, you said dissolving metals can also achieve the reductive removal of functional groups, like hydrogenolysis, but using electrons instead of atros.
Precisely. Halogens, for instance, can be cleanly removed using lithium or sodium metal, often in solvents like THF with T-butanol added as a proton source. Sodium in ethanol is also effective, especially for polyhalogenated compounds.
Any specific important applications?
A very common and synthetically important application is the dehalogenation of dihalocyclopropanes. These are easily made by adding dihalocarbines to alkanes. Treatment with sodium in ammonia or lithium in T-butanol removes the halogens, giving the simple cyclopropane derivative. You can even introduce deuterium specifically by using a deuterated proton source.
How does the mechanism work for halogen removal?
It's believed to involve initial electron transfer from the metal to the carbon-halogen bond, or the sigma orbital, forming a radical anion. This rapidly loses the stable halide ion, XO, generating an alkyl or vinyl radical. This radical then quickly accepts a second electron from the metal to form a carbanion, which is then protonated by the solvent or added proton source to give the final RH product.
Can other groups be removed this way?
Yes, phosphate groups can also be removed reductively. For example, vinyl phosphates, which can be made from ketone enolates, are reduced to alkenes using lithium and ammonia or ethylamine. This provides a two-step method for converting a ketone into an alkene. Similarly, aryl diethyl phosphate esters can undergo reductive cleavage, effectively removing a phenolic oxygen atom from an aromatic ring. Titanium metal, generated in situ, can also achieve these phosphate cleavages.
What about sulfur groups or other oxygen groups?
Milder reducing metals like metallic zinc, often activated as zinc dust, or aluminum amalgam, aluminum mixed with mercury, are particularly good for selectively removing oxygen and sulfur functional groups that are positioned alpha, directly adjacent to a carbonyl group.
Why are they good for alpha substituents?
The mechanism here is likely different, possibly a concerted two-electron reduction facilitated by the adjacent carbonyl group, leading to expulsion of the substituent, like acetate or a sulfone, as an anion. This allows for selective deoxygenation or desulfurization right next to a ketone or ester.
Are there other regions for removing alpha heteroatoms?
Yes, another extremely powerful reagent for this is samarium diodide. Cenarero. It's a strong, soluble, one-electron reducing agent that excels at removing alpha oxygen functionality. For example, it can reduce alpha-cetoxyketones to simple ketones, deacetylation, or even alpha-hydroxyketones to simple ketones, dehydroxylation. It's particularly useful in carbohydrate chemistry for modifying sugars and was famously used in a crucial deoxygenation step in the total synthesis of the anti-cancer drug Taxol.
Wow, semi sounds versatile.
Incredibly versatile for one-electron reductions. It can remove alpha-acetoxy, hydroxy, sulfonate, sulfoxide groups, even open epoxides reductively, or cleave certain ethers under the right conditions. A truly powerful tool. Hashtag 6.3, inductive coupling of carbonyl compounds, making CC bonds.
Our final category for dissolving metals is maybe the most exciting: reductive coupling of carbonyl compounds. You mean using these electron transfers to actually form new carbon-carbon bonds?
Exactly. Since these metals transfer single electrons, we generate radical intermediates, like those kettle radicals we discussed. Under conditions where these radicals prefer to couple with each other rather than being reduced further or protonated, you can form new CC bonds.
What's a classic example of this?
The classic example is the pinacol coupling. This is the reductive coupling of two molecules of a ketone, or sometimes an aldehyde, to form a 2,2-diol, which is generically called a pinacol. The original reaction involved treating acetone with magnesium amalgam, MgHg, to form two-color dimethylbutane 2-color pinacol itself.
Is pinacol coupling still done with magnesium amalgam?
Sometimes, but currently, the most versatile and dependable reagents for achieving reductive coupling of carbonyl compounds are various forms of low-valent titanium.
Titanium again. How is it used here?
Reagents generated by reducing titanium salts, like tickel or tickylo, with strong reducing agents like potassium, zinc-copper couple, or Li-H, create highly reactive low-valent titanium species, likely Ti0 or Ti0. These reagents are extremely effective at coupling carbonyl compounds.
What kind of products do you get with titanium? Diols like the pinacol reaction.
Depending on the specific titanium reagent and the reaction conditions, you can get either the TWUM2-diol, pinacol coupling product, or, often more usefully, the reaction can go further to produce the alkane formed by deoxygenation of the intermediate diol. This direct conversion of two carbonyls into an alkene is often called the McMurray reaction.
A Murray reaction. Okay, so titanium can make diols or alkenes from carbonyls. That sounds very powerful.
Extremely powerful. There are various recipes for generating the active titanium species. Some are better for intermolecular coupling, joining two different molecules, while others are exceptionally good for intermolecular coupling two carbonyl groups within the same molecule to form a ring.
Forming rings by coupling carbonyls.
Yes. Low-valent titanium, particularly the reagent prepared using a ZnQ couple, is incredibly effective at forming rings of all sizes: normal rings, 5-6 members, medium rings, 8-11 members, and even large macrocyclic rings, 12 members or more, with remarkable efficiency, often in high yield, even for strain systems where other methods fail. This has been widely used in natural product synthesis. People have even made wins with 36 or 72 atoms using this method.
Wow. Can it couple different carbonyls together, like a ketone with an aldehyde?
Yes, mixed couplings are possible, although controlling selectivity can sometimes be challenging. However, it has been successfully applied. For instance, a mixed reductive coupling using low-valent titanium was used to prepare 4-hydroxytamoxifen, which is the active metabolite of the breast cancer drug tamoxifen.
How is this thought to work mechanistically with titanium?
It's complex and likely depends on the specific reagent preparation. While originally thought to be purely surface reactions on titanium metal, studies now suggest that soluble low-valent titanium species, perhaps Ti2, might be involved. These species are thought to coordinate to the carbonyl oxygen atoms, accept electrons, and facilitate either CC bond formation to give a titanium pinacolate intermediate, which can yield the diol, or undergo further steps leading to deoxygenation and alkene formation. For intramolecular reactions, there's evidence for a template effect, where multiple titanium ions might cooperate to bring the two carbonyl groups together within the same molecule, promoting efficient ring closure.
And can samarium diiodide, 7-euro, do this coupling too?
Yes, semi-euro, being another powerful one-electron reducing agent, can also affect pinacol-type coupling of aldehydes and ketones, providing another useful method for forming these 1-Vero2 diol structures.
So there you have it, a deep dive into the fascinating, and I have to say, immensely practical world of reduction reactions in organic chemistry. From those intricate dances on catalyst surfaces to the precision steering of reactions with designer hydride reagents, we've really seen how chemists can transform molecules with incredible control.
Indeed. And I think understanding these mechanisms, whether it's a concerted hydrogen transfer like with Demamide, a stepwise electron addition from dissolving metals, or a free radical chain involving tin hydrides, it allows us chemists to not just predict what might happen, but to actually design synthetic pathways for really complex molecules.
Right. It really highlights how digging into the why behind the chemistry, the mechanism, allows us to achieve incredible feats. Things like creating life-saving drugs or engineering new materials with specific properties.
Absolutely. What stands out to me listening back is how a seemingly simple act, like just adding hydrogen or adding electrons, becomes so incredibly nuanced. You have all these different catalysts and reagents, each offering distinct powers of selectivity, choosing which group reacts, controlling the 3D outcome, even down to making just one specific mirror image form.
It's a real testament to the elegant complexity of molecular design, both in the molecules we make and the tools we use to make them.
And it's not a closed book either. The constant innovation in this field means new reagents, new catalytic systems are always emerging. Chemists are constantly pushing the boundaries of what's possible in synthesis, refining these transformations, making them greener, more efficient, more selective. It's an ever-evolving story of chemical ingenuity.
So maybe a final thought for our listeners. As you go about your day, perhaps consider this invisible world of molecules constantly being transformed, often through reactions just like these, one precise reduction at a time, building the world around us. What other seemingly simple chemical acts, maybe oxidation or addition, might hold such profound power to shape our world, if only we could master their hidden mechanisms as well as we've begun to master reduction.
A great thought to end on. Thank you for joining us on this deep dive into reduction reactions. We genuinely hope you feel more informed, maybe a little less intimidated by the complexity, and perhaps even a little inspired by the power and elegance of this chemistry. We really appreciate you being part of our last-minute lecture family.